So, can you actually trust your database to tell the truth? I mean, it sounds like a totally crazy question, right? But when you're building massive distributed systems, the reality of what is true and what is happening right now actually becomes incredibly blurry. We rely on data systems every single day, and we just kind of assume they give us this perfectly accurate picture of reality. But under the hood, it's a chaotic race against time, network failures, and honestly, physics itself. Welcome to this explainer. Today, we're getting right into the weeds of Chapter 10 of the classic book, Designing Data-Intensive Applications. We're going to tackle two of the absolute notoriously difficult concepts in distributed systems engineering: consistency and consensus. Here is our roadmap for today. We'll kick things off with the linearizability illusion, then we'll rethink the CAP theorem. After that, we'll look at ordering and logical clocks, followed by solving the consensus problem, and finally, we'll see how coordination services work in practice. Let's jump in. All right, Section 1, the linearizability illusion, or the mirage of a single copy. Okay, picture this highly relatable scenario. A referee updates a sports score. The leader database receives it, and Aaliyah reads from a follower node that's already processed that update. She cheers, her team won. But Bryce, who happens to query a different follower node just a fraction of a second later, gets a stale version of the data. His follower hasn't received the update yet because of replication lag, so to him, the game is still playing. Boom. The illusion of a single database is completely broken. So how do we fix what Bryce just experienced? Well, we need linearizability. This is basically the ultimate recency guarantee. It forces a complex, replicated system to behave as if there is only one single copy of the data. Basically, as soon as a write completes, every single subsequent read absolutely must return that new value. It beautifully hides all that messy reality of replication lag from the application. But here's the catch. Maintaining this single copy illusion is computationally expensive and widely sensitive to network delays. Moving on to Section 2, rethinking the CAP theorem, and why this famous rule is actually kind of flawed. Look, if you've been around system design at all, you've probably heard of the CAP theorem. It presents this classic, dramatic trade-off. If the network between your database nodes breaks, which is called a network partition, you are forced to make a choice. Do you choose CP, meaning you halt the system and return errors to ensure strict linearizable accuracy? Or do you go with AP, keeping the system available to process requests independently, but totally abandoning linearizability for eventual consistency? But here's the truth bomb from the source material. The CAP theorem is honestly incredibly unhelpful in practice. Why? Because network partitions are an unavoidable reality. They're a fault. They aren't some configuration setting you just get to toggle on and off. There's this great quote that sums it up perfectly. The only way you can guarantee no network partitions is by having no network. You don't just pick 2 out of 3. You're forced to choose between consistency or availability only when the network breaks. Plus, the scope of CAP is just way too narrow for modern engineering. To put this into perspective, look at the data from Google. Less than 8% of system incidents are actually caused by network partitions. Seriously, just 8%. The CAP theorem completely ignores other massive real-world headaches, like network delays, dead nodes, and slow application pauses. So while it's historically important, it basically launched the NoSQL movement, today we really need more precise ways to evaluate our systems. Which brings us to Section 3, ordering and logical clocks, establishing causality without perfect time. Here's the deal. Physical wall clock time is an absolute mess in distributed systems. Clocks drift, they jump backward, and trying to perfectly synchronize them over a network is a fool's errand. If we rely on physical time to order database writes, a super fast clock on one machine might overwrite a perfectly valid, newer write from a machine with a slow clock. To safely order events and figure out true causality, like what actually happened before what, we literally have to abandon physical time and adopt logical clocks. Enter Lamport timestamps. It's a brilliant mechanism, and it works in 3 simple steps without needing any perfect time synchronization. First up, every node just keeps a simple integer counter of the operations it processes. Second, it combines that count with a unique node ID, acting like a distributed ID generator to make sure every timestamp is globally unique. Third, and this is the really clever part, whenever a node gets a message with a higher counter from another node, it immediately fast-forwards its own local counter to match. Just like that, you've created a total causal sequence of events across your entire cluster. All right, Section 4, solving the consensus problem, getting independent nodes to agree. Imagine you're running a massive, complex, distributed transaction across multiple database shards. You immediately run into the atomic commitment problem. What happens if shard A successfully commits its part of the transaction, but shard B's network crashes and it rolls back? You're left with completely corrupted, partially applied data. It's a nightmare. To prevent this, we need an algorithm where all nodes agree to either entirely commit or entirely abort, with absolutely no middle ground. Now, this is where things get super fascinating. When you dive deep into distributed systems, you get this massive revelation. Single value consensus, appending to shared logs, atomic commitment, and linearizable compare and set operations. They are all mathematically equivalent. They are quite literally the exact same consensus problem, just wearing different disguises. If you can build a fault-tolerant solution for one of these, you can seamlessly adapt it to solve any of the others. And finally, Section 5, Coordination Services in Practice, bringing all this theory into the real world. Let's be real, writing a consensus algorithm from scratch is notoriously difficult and super bug-prone. Nobody wants to do it. Instead, modern architectures outsource all this heavy lifting to coordination services like Zookeeper, Etcd, or Consul. These tools package up all those highly complex, fault-tolerant consensus algorithms and just expose them as reliable, highly available services. They basically act as the central brain for your distributed architecture. And these tools pack some seriously powerful practical features. They manage distributed locks and leases, so you know for sure only one node is performing a specific task at a time. They support fencing tokens to protect your system from those scary zombie nodes that have paused and woken up late. They handle failure detection by demanding continuous heartbeats from clients, and they instantly fire off change notifications the second a node crashes or joins the cluster. But honestly, one of the absolute most common ways this gets used is for service discovery. In modern cloud environments, virtual machines are coming and going constantly. So coordination services step in to act as a dynamic registry. They automatically track which IP addresses are active, they allocate work to the healthy nodes, and they even elect new leaders automatically when crashes happen. They keep massive databases totally self-healing and operational, avoiding those dreaded split-brain scenarios entirely, and they do it all without any human intervention. Which brings us to our final thought for today. We've just seen how linearizability, logical clocks, and consensus algorithms all work together to create these highly reliable single-copy illusions in distributed systems. But you have to remember, this strong consistency, it requires constant coordination, quorum voting, and a whole lot of waiting on the network. So I'll leave you with this question to ponder for your next big system design. Is the inevitable latency and complexity of strict linearizability truly worth the trade-off for your specific application? Or can you safely embrace the chaos of eventual consistency?